Let's review gravitational potential and gravitational potential energy. Near Earth's surface, the gravitational field is approximately uniform. And let's say that two books are initially on the floor. They're going to be picked up and placed on a shelf 2 meters off the ground. One of them has a mass of 1 kilogram and the other has a mass of 2 kilograms. And in these problems, we'll round the gravitational field strength to about 10 newtons per kilogram. First, I'll calculate the gravitational forces acting on these books. The 2 kilogram book is going to have twice as much weight as the 1 kilogram. Let's do the calculations on the side. So the 1 kilogram book feels a force of 10 newtons pulling it down, and the 2 kilogram will feel a force of 20 newtons pulling it down. Next, we'll calculate the work done by gravity if these books are lifted vertically off the floor to the shelf. It's worth noting that in order to lift them, someone has to supply a force that is at least as big as the gravitational force. I'll call that the force of push. And it has to be 10 newtons for the 1 kilogram book. And it's got to be 20 newtons for the heavier book. The reason I bring up the force of the push is that when a person lifts these, they are going to do positive work because they're pushing upward, and the boxes actually are going to go upward. The red represents their displacement. We could call it a delta y. And the delta y is 2 meters. So when we're calculating the work done by the first person who's pushing will be 10 newtons times 2 meters, which will be 20 joules. But the work done by gravity on that first block will actually be negative 10 newtons times 2 meters, negative 20 joules. Now, what reasoning can we give for this? Well, there's a formula for work. Work is a dot product between a force and a displacement. If you push upward and the box actually goes upward, then you're doing positive work. But when a force pulls down and a box doesn't go down, but it goes the opposite direction, that's when negative work gets done. How can we evaluate work? Well, we could use this dot product formula. It's the magnitude of F times the distance that it travels times the cosine of the angle between the force and the displacement. If you need a review of work, feel free to check out my Physics 1 playlist. There's several videos on that topic. This is just a brief review. I'll calculate the work done by the second person who pushes upward. This time, I'll use the dot product formula. We said that the person will push with 20 newtons. The distance the person pushes is 2 meters. And now we'll put the cosine of an angle. The angle to use for the person pushing is 0 degrees. This is because the angle between these two vectors is 0. They're both pointing upward. We'll get a positive 40 joules for the person who's lifting the book. But when we calculate the work that gravity does on that book, it's the magnitude of the gravitational force times the distance the book travels, and then we'll use cosine of 180. Why is it cosine of 180? Because gravity pulls down, but the book doesn't go down, it goes up. There's 180 degrees between the directions of those vectors. So gravity does negative work here. All right, so what if instead of moving the book straight up, let's say that they're moved along a diagonal path like this. Where our delta R is not exactly vertical or horizontal. It's at a weird angle. There will be a delta X of 2 meters and a delta Y of 2 meters. We'll calculate the work done by the gravitational force. Now gravity is going to be pulling downward. And the displacement vector is at a 45-degree angle. If we want the work done by gravity on book 1, then we could use the magnitude of the force, which is 10 newtons. And then we can multiply by the displacement here, which will actually be 2 radical 2 meters. And then we need a cosine of an angle. The angle to use is the angle between the force and the displacement. That's a 135-degree angle. If we calculate this, the work done by gravity is still negative 20 joules, same as it was above. So it didn't matter that the book had moved horizontally. All that mattered was its vertical displacement. And so that's why we often use this formula for objects near Earth's surface, that the work done by gravity will be negative mg delta y. Let's try calculating it with that formula. We'll use the mass of the book, gravitational field strength, and the vertical displacement, which here will be a positive 2 meters because it's up, and conventionally up is the positive y direction. So this formula also gives us the same answer of negative 20 joules. Using that same formula, the work that gravity does on our second book, the 2 kilogram book, will be negative 40 joules. So 2 different ways of calculating work done. Now we want to find each book's change in gravitational potential energy as a result of being lifted vertically off the floor to a new position. When the book's on the floor, the formula we would use for initial gravitational potential energy will be mgy. Then it's going to move to a new position, and we'll call the new gravitational potential energy UGF. In order to use these formulas, we have to establish a coordinate system. Let's let the positive y direction be up. And let's let our book start off at a y of 0. If that's the case, then our initial gravitational potential energy will be 1 kilogram times 10 newtons per kilogram times 0, which is 0. And our final gravitational potential energy will be 1 kilogram times 10 newtons per kilogram times 2 meters, which is positive 20 joules. The change in gravitational potential energy, therefore, is UGF minus UGI, which is 20 joules minus 0 joules, which is 20 joules. That was for the first book. Let's do it for the second book now. Our UGI will be 0 because it's on the ground, and that is designated as a y of 0. When it's raised to a position of 2 meters, our UGF will be 2 kilograms, 10 newtons per kilogram, 2 meters, 40 joules. So our delta UG for book 2 will be 40 joules minus 0 equals 40 joules. Going off the formula UG equals mgy, we can also form the useful formula delta UG equals mg delta y. Let's see if this would work for our 2 kilogram book. Delta UG equals 2 kilograms, 10 newtons per kilogram, 2 meters. It works. The next thing to look at will be gravitational potential, which is similar to potential energy, but it's potential energy per unit mass. Calculate delta Vg between the floor and the shelf for each book. And what does delta Vg really depend on? One way to calculate a gravitational potential value is to divide the potential energy of an object by its mass. So let's do that for the first book here. We said that when the first book was raised up to a height of 2 meters, it would have a gravitational potential energy of 20 joules. And we said that the other book would have a gravitational potential energy of 40 joules. So if we divide the gravitational potential energy gained by the mass of that book, we get 20 joules per kilogram. So let's write that down. Now if we calculate the gravitational potential for the second book, we would get 40 joules over 2 kilograms, which again is 20 joules per kilogram. Both of these objects went from a gravitational potential of 0 to a gravitational potential of 20 joules per kilogram. So the Vg values depend only on position. They don't depend on mass. So what we can draw are what are called equipotentials. And we'll typically do that with dashed lines. This is an equipotential, meaning that all objects that are on that line are at the same gravitational potential, 20 joules per kilogram. And similarly, all objects that are on this dashed line are at the same potential as well. This is the 0 joule per kilogram equipotential. In a uniform gravitational field like this, we can create as many equipotentials as we wish, and we can label them. These values tell us how much potential energy in joules is required per kilogram to lift objects. If we take the gravitational potential energy formula and divide both sides by the mass, we will arrive at the gravitational potential formula, which is simply G times Y. So gravitational potential only depends on the field strength and the position in the field. And to finally answer the question, the delta VG for both books is going to be 20 joules per kilogram.